All right. These are spin products. There are 3 electrons. And we can write this as just suppressing the electron labels, alpha times alpha times alpha. This means the same thing as this one. In other words, from left to right, 1, 2, 3. These are the electron labels. In general, in a spin product, sum of ms values of spin functions, of one electron spin functions, one electron spin functions are either alpha or beta. Ms value for an alpha spin function is 1 over 2. For a beta spin function is minus 1 over 2. There are just 2 values. All right. So here, ms, total ms. What is the small ms for the first factor? 1 over 2. For the second one, also 1 over 2. For the third one, 1 over 2. So net result is 3 over 2. For the second one, this time all of them are minus 1 over 2. So here we have minus 3 over 2. Minus 1 half plus minus 1 half plus minus 1 half. Now, next you ask, what could be S value? S must be larger than or equal to ms. In this case, largest value for ms is 3 over 2. Therefore, S has to be 3 over 2. Both this spin product and this spin product correspond to S equals 3 over 2. This is quite simple. You may have more than 3 spin functions, 4, 5, 6. The procedure is same. Total ms is sum of small ms values, and similarly for the orbital products. We have discussed 2 electron orbital products, but you may imagine 3 electron, 4 electron, 5 electron orbital products. To get the ml value, total ml, you just add up the small ml values of each orbital in the product. Any other question? Five. This is about boron atom. Write the electron configuration. Electron configuration for the ground state. You have learned this in general chemistry course. We start with the 1s orbital, and because we are interested in the ground state, place 2 electrons into the 1s subshell. There are 5 electrons. So we take the next one, 2 more electrons there. 2 plus 2 is 4 electrons so far. We need one more electron, and that one we place in a 2p subshell. This is the electron configuration for the ground state. This was part I. In part double I, now find the energy associated with this configuration, assuming repulsions among the electrons can be ignored. If the interactions among the electrons are ignored, that means we have 5 independent electrons. 5 independent electrons. When electronic repulsions are ignored, it means 5 independently moving independent electrons moving around a nucleus with charge. What is the charge on the nucleus of boron? Atomic number, isn't it? +5. Now, because the electrons are independently moving, it means each electron is moving around a nucleus with +5 charge independently of the others. In other words, for a single electron, it's a hydrogen-like atom for a single electron. Hydrogen-like atom. The energy expression is minus z square over 2 times n square. Or in our case, z is 5 minus 25 over 2 times n square. N is 1, 2, 3. This is in Hartree. The energy unit is Hartree. So, what does it say? Find the energy. Find the total energy. There are 2 electrons in the 1s. What is the energy of the 1s? N equals 1. So it is minus 25 over 2. There are 2 electrons, 2 times that. Plus 2 electrons in the 2s. N is 2 minus 25 over 2 times 4 plus 1 electron in 2p. 2p energy is the same as this one. So, okay, there is plus minus 25 over 2 times 4 also. So this is the total energy that we may call core. This word we had introduced before. When the electron-electron interactions are ignored, the remaining part of the Hamiltonian is called core Hamiltonian. The energy related to the core Hamiltonian is called core energy. So you may do the rest, or I will do it for you. This is minus 25. This is 12.5 divided by 2 minus 6 point, and this is half of this number, minus 3.06. So 21, 30, 31, 25, 31 plus 3 minus 34. Hardly. This is the energy, total energy of the 5 electrons when we ignore electron-electron repulsions. Of course, the true energy will be much larger than this one because electron-electron repulsions will contribute positively. They will increase the energy. What will be the first ionization energy of boron within the same approximation? Just think about what is ionization process. It is this. Ionization energy is the energy of the cation, lowest energy of cation, this part, in which the kinetic energy of electron is taken as 0 because it is the minimum amount of energy needed to expel the electron by definition of ionization energy. So energy of the cation minus energy of the neutral. Well, we may take the electron, remove the electron either from a 2p or 2s orbital because they have same orbital energies. So the cation has electron configuration this is the electron configuration of the cation in which I have taken the one electron from the 2p subshell. So the energy difference between this configuration and that configuration is the energy of 2p. So this energy is minus 25 over 2 times 8, 2 times 4, n equals 2. Did you understand? The energy difference between the cation and the neutral, within this approximation, electron repulsions are ignored, is the total energy of this one minus total energy of that one. But because these parts are the same, they will cancel. So the net result is minus the energy of 2p. But 2p energy is already minus, so minus 2p energy is a plus, positive number, as you see here. Within this approximation. This is about the vibrational potential energy function for a diatomic molecule. It says plot a qualitative graph of potential energy V for versus R, for R ranging between 0 and 10 angstrom. Qualitative, so oh, there is a, I have started from the middle of the problem. I was looking for the definition of the function. There is a approximate but useful vibration potential energy function given. This is A times 1 minus e to the minus b r minus c. And then this is squared. A obviously has energy unit. It is given 4.75 electron volts. B, what should be the unit of B? If R is in angstrom, B should be, B times R should have no unit because it's in the exponential. Therefore, B must have 1 over angstrom units. It is given as 1.94 angstrom, 1 over angstrom. What about C? What should be the unit of C? R is angstrom. C should also angstrom. It is given as 0.74 angstrom. It says plot a qualitative graph in which R ranges 0 to 10 angstrom. This is R. This is this expression. Qualitative is quite simple. Notice that if R is equal to C, then this is 0 here, right? 0. E to the 0 is 1. 1 minus 1 is 0. So there, at R equals C, say, what is C? 0.74 R in angstrom. This is 0. As R, when R is larger than C, then R minus C is a positive number. But there is a minus here. In other words, e to the minus x, for as x gets larger and larger positively, e to the minus x gets smaller, isn't it? So, when R is larger than C, this part, e to the minus b times R minus C is getting smaller and smaller as R goes larger. If R is very large, then you may ignore C with relative to R. Then B times R will be very large, but there is a minus sign here. It corresponds to what happens when x is very large. What happens? E to the minus x becomes 0. So, for very large values, this becomes 0, and the value of the potential is just A. It corresponds to, and then, of course, when we say very large value, it starts, now, suppose this is a large number. Even 10 angstrom is large, all right? If at 10 angstrom, this part is very small relative to 1, then at larger R values, 15 angstrom, 20 angstrom, it is near 0, which means for large values of R, it's flat. When R, we know that at R equals C, it is 0. Now, on this side, when R is smaller than C, then the number in the parentheses will be a negative number. But there is a minus here. Minus times minus plus. So it corresponds to e to the plus x case. This part is going to decrease this value from A, of course. But how is it going to look like? Then at r equals 0, this is e to the b times c. So this value here is a times 1 minus e to the b times c square. B is here, C is there, so you can calculate it with A. Qualitative. We see that there is a minimum. Where is the minimum? At R equals 0.74 angstrom. The minimum in the vibration potential energy function gives the average bond length. In fact, these parameters are for the hydrogen molecule. It is not stated, I think, here, but the numbers are experimentally obtained for the hydrogen molecule. The equilibrium bond length, this is Re. What is the value of the electronic dissociation energy? Electronic. By definition, the electronic dissociation energy is this difference, or the value here, because the lowest value is 0. What is the asymptotic value for potential energy when R becomes very large? It is just A, isn't it? So this is 0, this is A minus 0 is A. So this electronic dissociation energy is simply A. What is the value of A? 4.75 electron volts. This is the electronic dissociation energy. The last part is asking us if this expression here has a name. This is called Morse potential. All right, so keep in mind that, because if you want to look for it in the internet, for example, you should know the name. If you enter Morse potential, you will obtain information about this function. If this potential function is approximated by a harmonic oscillator. What is a harmonic oscillator? Harmonic oscillator has this form, 1/2 k times x square, where x is r minus Re. So, if we fit this function to a harmonic oscillator, and the fitting point should be near the minimum, this is the harmonic oscillator. It says derive an expression for the force constant, K. This K is, you can see it from here also, second derivative of V with respect to X, evaluated at X equals 0. X equals 0 means R equals equilibrium bond length. But because the relation between x and r is one-to-one relation, this derivative is, when applied to that function, is the same thing as taking the derivative with respect to r. Now we can say evaluated at r equals re. So we are going to first take the derivative of it, of that expression. What is the first derivative? A times 2 times 1, the fact, remember it's the square, 1 minus e to the minus b r minus c times derivative of inside. This is derivative of that is 0. When we take the derivative with respect to r, there is a minus here, so they will cancel. B will come here, b times e to the minus b r minus c. This is the first derivative. Now we opt to get the second derivative. I will take the derivative and then substitute r equals r0 immediately to simplify it. So we have this part. This is 2a times the derivative of inside, in which b comes, minuses cancel, times e to the minus b times r minus c, and there is this factor. So this becomes b squared. This becomes same factor, so put a 2 here. But remember, r equals re means c. R equilibrium is the value of c. So when r is, we set r equals re, this means r equals this c, because re, equilibrium bond length, is equal to c. This becomes 0. E to the 0 is 1. So from here, the net result is 2a times b squared, after putting r equals re. Now there is also derivative, this part times derivative of this. But this, it will not make any contribution to here, because this part, when you put r equals c, e to the 0 is 1, 1 minus 1 is 0, 0 times anything is 0. So the net non-zero result is this. Let us write it. 2 times a times b squared. Now, what is the numerical value? We just put the numbers. K is equal to 2. This is K. A is 4.75 electron volt. We convert this into, the problem is asking us, what is it, what is the numerical value of force constant, K, in Newton per meter unit, which means in SI unit. Our energy here is not in SI unit, so we convert this into joule. How do we do it? By multiplying with elementary charge. EV is the same thing as the elementary charge, 1.602 times 10 to the minus 19 coulomb. That is the conversion factor into joule. So this is 2 times 4.75 times 1.602 times 10 to the minus 19. This gives, converts it into joule. Multiply with B square. B is 1.94 angstrom, per angstrom. 1.94. Angstrom is 10 to the minus 10 meters. 1 over. And then take the square. So we can see that, let us simplify a little bit. After squaring, this is 10 to the minus 20. Here we have 10 to the minus 19. Right? So the net result is 2 times 4.75 times 1.602 times 1.94 square divided by 10. So use a calculator, and the unit here will be automatically Newton per meter, because we have used SI units everywhere.
Elektron voltu nasıl metre çeviriyorsunuz?
Şurada söylüyor size. E'yi görünce E'nin sayısını alacağız. Because E times 1 volt is EV. E, tabii. Bunlar hep çarpıdır zaten. Öyle okumanız lazım. 4.75 çarpı EV. EV neyse koyacaksın yerine, çarpacaksın. EV de zaten şu. This is E times 1 volt. Evet. We have to convert everything into the same set of units because the question is asking us to find K in Newton per meter or joule per meter square. Look at here. This is meter square in SI unit. Unit for K must be energy per square meters because the left side is energy. And if this is joule, then unit of K should be joule over meter square. It is the same thing as Newton per meter. You can see it from here. The force corresponding to this expression is minus derivative of this, first derivative with respect to x. It is K times x minus. Now, the SI unit for force is Newton, isn't it? X is meters. Therefore, unit for K should be Newton divided by meter. It is the same thing as this unit. Joule over meter square. You can see it is joule over meter square from this expression. You can see it is equivalent to Newton over meter from this expression. All right. Well, I think this number is, if this number is correct, you should obtain from here 573 Newton per meter for this calculation should give 573 Newton per meter. Force constants in Newton per meter are about this range, 400, 500. In other words, they are not very small. They are not like 0 point something, or they are not 10. They are hundreds, several hundred, depending on which molecule you are talking about. We have time for another question. Which one? We have to indicate it here, level numbers, levels, first level. This is E in wave number units. First level is taken as the reference 0. Second level is 557.1 wave number above it. Third level, 1410 wave number in energy. Fourth level, 7125.3. And the fifth level, what is this? 16,367.3. First, information about first 5 levels is given to us. Also, degeneracy information. The lowest level is non-degenerate. Next one is triply degenerate. This one and the next one is 5-fold degenerate, and the last one is singly degenerate. Now, this is the data given. We are asked relative populations. Relative populations at which temperature? 20. At 20 degrees centigrade. Well, this is an application about Boltzmann distribution. What is Boltzmann distribution? Population of the jth energy level is equal to a constant times degeneracy of the level times Boltzmann factor. What is Boltzmann factor? E to the minus energy of the level divided by kT. This is Boltzmann constant here. This is T is the absolute temperature. What is absolute temperature if this is in centigrade? 273 plus. So this is 293 Kelvin. Relative population is relative to the lowest level. So here we have Nj over lowest level. The purpose of relative population is to get rid of this constant here, because when we divide, the constant will disappear. This is and this is okay. Next, you apply this expression to the numbers over there. Because the energies are given in a wave number unit, instead of converting everything into joule unit, we are dividing by kT. kT is also energy. We first calculate kT in joule and then convert it into wave numbers. kT, Boltzmann constant is joule per Kelvin. T is 293 Kelvin. The net unit here is joule. How do we convert it into centimeter minus 1 unit? divide by hc. C is in centimeter per second. So, if this expression is divided by hc, 6.626 times 10 to the minus 34 times 3 times 10 to the 10. All right? Then do the calculation. Let us simplify it. This is after multiplying with 10 minus 24. You can cancel it with above. So what happens is this is 1.381 times 293 divided by 3 times 626. There is a 10 to the minus 1 here. When we take it up there, multiply it with 10. So use your calculator and obtain the KT value. Do you have a calculator? I didn't bring mine. Yazıyor mu? Heh. So, first calculate, well, relative population. This one is directly 1, of course. It is n1 over n1. This one, degeneracy is 3. So you will do this, 3 times e to the minus 557.1 divided by 203.8. Do this calculation. And the result is going to give you the relative population of this second level. And according to the here, 0.195. So it means the result of this calculation should give 0.195. Then repeat the same thing with this level here. Degeneracy is 5. Remember, degeneracy G1 is 1, so it's not included. For the second one, it is 5 times e to the minus 1410.10 divided by same number, 203, and do the calculation. According to here, you should obtain 0.005. So the relative population is 0.005. Already here, relative population is very small. For the remaining ones, energy is even higher, so the populations will get very small. In fact, approximately zero, and this is the reason why we don't need information for higher energy levels, because their relative populations will be negligible. Then calculate the percent population in each energy level. From the relative populations, we can obtain the percent populations. Percent population is relative population divided by sum of relative pops. This calculation is going to give you a number between 0 and 1. Percent means just multiply the fraction with 100. So if you multiply it with 100, you will obtain it. So let us look at the sum. 1 plus this plus that. What does it? 1.2, isn't it? This is the sum. 1.2. Percent population of the first level is 1 over 1.2. times 100. Percent population of, this is percent, of this level is 0.195 divided by 1.2 times 100. And the percent population, so it appears this is 83.3%. This is 16.2%, and the calculation here is 0.005 divided by 1.2 times 100, and here 0.4%. So 83% of the molecules are in the, or atoms, are in the lowest level, ground level, at this temperature. 16.2% of the molecules in the sample are in an excited energy level, which is 557 wave number above the ground level, and very little in the next energy level, and none at all in the higher energy levels.